Okay, in this video, we're going to take a look at some more hypothesis testing using the z-test. In our last video, we took a look at using a two-tailed hypothesis test. Now we're going to look at a one-tailed hypothesis test. So, example 4, a company claims that their program will increase your grade in statistics class by at least 10%. Oh, that's very nice. That'd be great if it works. You think it might not be that much, so you obtain a sample of 40 students and find that the sample mean increase in grades for the class is 9%. So assuming a population standard deviation of 3.75% and the population data is normally distributed, test the claim that the mean percent increase in score is less than 10% at the 2% level of significance. So alpha, this case, is 0.02. So we've already taken care of our assumptions, and again, just to reiterate that the data is normally distributed, and we have a sample size of at least 30. So now let's look at our null and alternative hypothesis. So the null hypothesis is the one that represents equality, and that's, in this case, the company saying that their program is at least 10%. So that could be 10% or it could be higher. Certainly, they're not going to feel bad if it does increase your statistics grade by, let's say, 30%. That would be great. But 10% or higher, so greater than or equal to 10%, is our null hypothesis. And then we're testing the claim that it might also be less than 10%. So we have a null hypothesis of 10% equal to 10% increase, and the alternative is less than 10%. Now, again, truthfully, there's nothing wrong with saying the null hypothesis is greater than or equal to 10%. The alternative hypothesis is the one that's going to help us determine our p-value and confidence interval and things like that. So don't worry if you have equal to or greater than or equal to for the null hypothesis. That's great. Either one's fine. Less than 10% is the alternative. All right, so if we draw a normal distribution, the 2% significance level, if we look at having a 2% area to the left, because it is less than, it's a left-tailed test, to the left is going to give us a z-score of negative 2.05 for our critical value. And again, we can get that by, we're working with z-scores, and we're given an area, so go to option 2. And then it's the area that's to the left, option 1. And we said that the area, the significance level, is 2%. So this red area represents 2% of all the values underneath this curve. So in this case, our area is 0.02, which gives us a z-score of negative 2.054. So I just rounded it to 2 decimal places here, negative 2.054. So anything less than that will get rejected as a test statistic. Anything greater than that will not get rejected. So our test statistic is going to be our sample mean here, which is 9%, minus the population mean of 10%, all divided by the population standard deviation divided by the square root of our sample size of 40. So in this case, it's our 9% minus the claim population mean of 10%, all divided by 3.75% as a decimal is 0.0375, and divide that by the square root of 40 to get our standard error highlighted in blue here. So 9% is our sample mean, 10% is our population mean, and then our standard error, 3.75%, 0.0375, divided by the square root of 40, that gives us a z-score of negative about 1.687. And 1.687, negative 1.687, in terms of visually, would probably be right about here. Notice this, where I have the mouse cursor here, is not in the red rejection region. So according to our test statistic of negative 1.687, and was that the? Yeah, negative 1.687, when we compare it to negative 2.05, and it is a left-tailed test, it is not in the rejection region. If we want to find the p-value for this, we can take this z-score, this negative 1.687, and we can find the area now in the p-value. So if we go working with z-scores, this time we're trying to find an area, a probability or percent, a p-value. And it's the area to the left. And the z-score we said was negative 1.687. So negative 1.687. And we get about 0.0458 as our p-value. So in terms of this, if they're negative 1.687 is here, then everything to the left of that is about 4.58%, which is greater than the 2% in red. And then finally, our confidence interval. If we construct our confidence interval, we have our x bar is 9%, 0.09, our sample mean, our sigma value 0.0375, 3.75% for the population standard deviation, sample size of 40. Remember, for confidence intervals, if we use the confidence interval code from before, pardon me, we can't do a 98% confidence level. 100% minus 2% is 98. Because it's a left-tailed test, we have to double this significance value. So when we double 2%, we get 4%, and that's actually going to give us a confidence level of 96%. So again, if it's a left-tailed or a right-tailed, and you're going to use the confidence interval approach, then especially if you use the code from our confidence interval section, take whatever the significance level is for left and right-tailed, and then double it, and then your confidence level is the complement of that. So again, if we double 2% level of significance here, we get 4%. The complement of 4% is 96% or 0.96. So when we run this code, we get between 0.0778 and 0.01 or 0.1022. So our test statistic is outside of our rejection region. Our p-value that we calculated is greater than our significance level. Our confidence interval does contain the population mean, so all three lead to the same conclusion. Do not reject the null hypothesis. So we can conclude at the 2% significance level, we don't have sufficient evidence to reject the claim that the mean increase in score is 10%, and thus there's not enough evidence to conclude that the mean increase is less than 10%. So again, if we wanted to run this test again, we'd probably get different results in all likelihood. I would recommend having a larger sample size. That's usually the best way to get better results, is to include more of a larger sample of the representative population. So, all right, that about does it for this video. Thank you for watching. I'll